management, even AEs. So that's not the focus. I'm going to talk about performance, hardware for performance. And even here, this is something that I need to distinguish between, I guess that for all of us, we have talking already accelerators for AES and other cryptography primitives. So I'm talking about performance acceleration, but for fancy cryptography. So what is fancy cryptography? I took some definition from the fancy cryptography repository, which I encourage you to check. But let's just stay with the intuitive definition. If you think you work on fancy cryptography, it is likely fancy. Okay? Right? ZK for homomorphic encryption, and so on. Why we are focusing on this type of cryptography? And it's a simple reason. Privacy enhancing technologies have high demand these days, right? Think about AI, we need some kind of like balancing force to that. Today when I speak with AI, if I used to, when just searching, I used to basically give advice how to write a board deck. Now when I ask, tell me how to write, if this board deck is good enough, or let me how to improve it. And these PETs, privacy enhancing technologies, are notoriously slow, right? And we need to figure out a way to still work with these technologies. So today I'm going to present Bicycle, and before going to present it formally, I want to start by explaining about hardware for cryptography in this context. So on the right we have, on the left we have the green. This is the accelerator no-cap architecture, a recent paper from Sweeney at MIT and co-authors. And that's amazing, right? Think about it. It's a whole architecture for Goldilocks spine, supports ZK, state-of-the-art protocols like Spartan and Orion natively, has building blocks for primitives that are compute intensive, like circuitries and entities. Now, this is something that appears only on paper. We do not have it. What we have instead is what you see on the right, which is, in this case, TPU. And TPU is fantastic, right? This is like one of the greatest, probably, inventions of the past few decades. But it is completely different, right? So floating point, 16 bits, some compiler that doesn't really like cryptography. It excels because they have this like nice historic array, they have some vector operations and matrix multiplication that is very efficient. So this slide raises two important questions. One is why cannot we cannot get the hardware that we deserve? And this is a question I'm not going to touch in this talk. It has a lot to do with market supply and demand and how you build chip companies. But right now, let's assume that this will come in the future. The second question, which I'm going to explain how we solve, is what we can do with the hardware that we are given, right? With these amazing TPUs. By the way, this is a super interesting paper about the TPUs if anyone wants to learn more about that. So before explaining the solution, I want to spend a little longer on the problem itself so that I can bring it home. For that, I want to introduce the concept of hardware lottery. Might be slightly abusing this concept, but basically, Sarah Hooker a few years ago in a nice paper introduced this term, coined it, to explain that if you want your research to be impactful, to have some chance to go mainstream, you need to be aware of the software and the hardware that you are implementing on. So one question is, how can we make our ideas based on merit alone? But the truth is that we do need to have this kind of hardware and software awareness. Think about NVIDIA and AI today. If you cannot express your algorithm in CUDA, then you're not going to publish the paper, okay? So one example here is this paper from 2022, Hyperblock, which is, like, again, amazing idea that was timely, but And one thing that they introduced is replacing entities with sum checks, right? And the problem is that entity is something that is well studied in terms of hardware. But sum check, we are not really familiar with it, at least not when this paper came out. And as you can see on the right, is that when you look at the properties on how to run sum check in hardware, it's not really efficient. It's like memory bound in the sense that, actually this is a nice image on top. It has like 3 parts, right? So sum check, on the x-axis you have the number of rounds, and the problem kind of like scales down the more you make progress in solving it. So at the beginning you can see you are very much memory bound, and then as you make progress, you need less memory, so then compute starts to become more interesting. And then at the end, when the problem is kind of small, you don't really need too much memory, but you also don't need compute. You can see it also from the graph below, where the L1 cache starting to become way more active. So indeed, the authors, right, this is like Hyperplot is from Vinny Chen, Benedict Boots et al. They, or some of them, a few years later, came up with a new paper that deals with the exact details of hardware for Hyperblock, which is necessary, as I mentioned. So how do we solve this problem? How do we make papers that consider software and hardware as an integral way? And one way is by injecting money. So this is DARPA for fully homomorphic encryption. There are multiple startups that started building FAG hardware because of DARPA. There's Z-Price for ZK. And what I suggest here is Icicle, which is this platform that allows you to write software and hardware, or to design your algorithm being aware to software and hardware. So Icicle is a library for high-speed cryptography. And I want to start on the left by explaining the very simple design of this library. So we have frontends, right? So this is different languages that you as a cryptographer can use, right? So this is a product for cryptographers, library for cryptographers. C++ used to be a very popular choice. Nowadays, recent years, we have Rust, we have Go. Hopefully in the future we'll have Python, right? You just want to get something sweet, kind of like some part of your protocol, just go ahead and script it. And using a bunch of APIs, developer can, or cryptographer can write his algorithm. So think about the algorithm you see in your paper. You just want to be able, as simply as possible, to translate it into software. So on the left you can see, I continue the sum check example, right? And what you can notice is that first you don't see anything that mentions the hardware. So this code can run on CPU, can run on GPU, can run data center, can run at the edge. You can just choose at the level of like granularity of line by line where you want to run it, but when you code it, you don't really need to be aware. This specific sum check, sum check can run on any MLE, so we had to come up with an API that allows you to program whatever expression of polynomials. And we also have some predefined expressions. This one is the equal times AB minus C. And then you have the backend, which we want it to be modular, right? So every hardware vendor can plug in their own hardware. If it's like ZK acceleration, FAG acceleration, HPC, TPU, and so on. And I think this part is actually, we kind of like figure it out in a nice way, because we do see that anyone today that thinks they have hardware that can contribute to cryptography basically just plugs it in, and then all the code can just run natively on this hardware. And I think the biggest unlock of this design is that you don't really need to start with a bulky GPU next to you to code for GPU. Right? You can just use your Mac, right? Code something, run it in CPU, and then when you are ready to test, you can then you can plug the GPU. Okay, so the onboarding is super easy. And then you can see the figure here at the bottom, which shows you the same code both on CPU and on GPU. Obviously, GPU is way faster, but that's not necessarily the point here. The point here is that same code would run on any platform. Now, if this is a product for cryptographers, you might ask, how can we test it? So we've done the following, which is very simple. We, this year and also last year, we had a grant program where we said to cryptographers, choose a paper, go to ePrint, choose any paper you want. And re-implement it using Icicle, and we're going to pay you based on how much performance you're able to get. And we learned a few things, right? So on top you see the work done by Google from Berkeley, taking threshold encryption papers that he wrote and then ported to Icicle. So one thing is that we learned that Icicle can also accelerate threshold encryption, which is nice. And also, I mean, I don't know if you see the numbers, but trust me that for different sizes, the Icicle CPU and GPU backend are way faster by orders of magnitude compared to the paper implementation. At the bottom, we have another example, another grantee that, from China that implemented collaborative SNARK. And just to complete the picture, when talking about the software and APIs, as a cryptographer, what you get is this list, right? So this is for the C++, and you can either use vectors, polynomials, matrices, and for some specific heavy, compute-heavy problems, we have special treatment for these like compute-heavy primitives. And then you can even go further. So right at the bottom, you can see the menu we have for lattice-based cryptography and what you can do to use it to implement your lattice cryptography. So in the next few slides, I'm going to quickly cover different aspects of the software that we developed and how we scaled it over the last year or so. But before that, I want to explain what goes inside. How can we, what does it mean to run all of this stuff natively in hardware? So it's easier to explain what you see on the right, which is take these compute-heavy problems, MSN, NTT, subject, and implement specialized algorithms for them, which is something that was not really, not done extensively in literature so far. And this is interesting, you know, you want to run something efficiently on TPU, you need to spend some time doing that, learning how to do it in the proper way, and sometimes there's a nice algorithm that can make a research paper. Another thing is that, as I showed you before, on TPU, for example, it is a 16-bit floating point, right? But the point here is that sometimes you actually want to go and define new fields, right? So we also came up with hardware-efficient fields. Now we also have baby quad, which is an efficient ring that we came up with. And even just explaining the arithmetic of this like very special primes is useful. I mean, this Mersenne thing came out to be super popular because just people were not familiar with how to do efficient arithmetic on hardware with this. Finally, sometimes you actually need to go all the way back to the algorithms that no one thinks that they can be changed and just improve them. So even modular multiplication that you can see here. Now, how can we go from here? So I want to explain how we grow the software vertically and horizontally, and for that, let me just give you a quick mental view of the steps. Right? So at the very bottom we have the hardware, then we have math, right? Primitives, this is kind of like where we are today. Then you can build protocols like ZK, FAG, and then you have applications. Obviously there's like, the higher you go in the stack, the more you have. Right? You have infinite applications that can run on a discrete number of, let's say, ZK protocols, which in turn run on a smaller number of primitives, NTT, MSN, and finally it runs on very, very small number of hardware devices and accelerators. So one way we can go is vertically, right? So I'm not going to describe what we've done going downwards, implementing hardware, but going upwards seems very natural. Just implementing stuff using implementing protocols. Here you see on top left, Code 16 and then Halo 2. In both cases, obviously, it runs natively in hardware, so you can see that on GPU it's like way, way faster than anything that existed before. And this is, by the way, this is obviously open source, so if you write software for cryptography, it should be open source. And yeah, I mean, many people are using it. Another thing is to go horizontally. So let's just add more cryptography. So earlier this year we added PQC. So here is a figure that I like, showing how we outperform NVIDIA on CU PQC library. Now we actually also replaced or integrated with OQS. With OQS, this is the Linux Foundation library, so MLChem is now going to be integrated there. And then just lattices, ZK lattices, which seems to be have a growing interest in the community. So this is where you can see how we implemented Labrador end-to-end using Icicle. Another thing that you can do is to go to the edge, right? So we decided to take one of our provers and adapt it to run on mobile, specifically on mobile. So it's called IP1, Ingonyama Mobile Prover 1. It's based on Goat 16, and it already achieves very nice numbers, right? So you can see the figure on top that for 1 million R1CS constraints, you get like 10 seconds running time, right? Below you can see that for real-world applications, like Haribo that is using this product, they get 2.3, up to 2.3 seconds for their use case, right? Which has good user experience in that case. One thing to note here is that to make sure something running nice on the edge, as opposed to just like running it end-to-end on GPU, here we need to take advantage both of the CPU and the GPU, right? So Metal is the iOS GPU and Vulkan is for Android. So here we took advantage of the R backend and also of the Metal, in the case of iOS backend. And yeah, finally there are some multiple real-world examples. If it's L2s like Jolt, Eigenlayer, so now it's 100 megabytes per second. I can tell you, but they're running on many GPUs. Done an amazing job using Icicle. Taught me that you could just, build stuff that I never imagined is possible. Zero base, Starcoil, all of them compared to what they had before, and now they leverage the library. Yeah, that's it. And just want to mention, this came, the email from the right, just like added it a few minutes ago. Another way we support cryptographers is just by allowing them easy access to GPUs. I should probably add the responsive that we sent just a minute after with an access to a machine with 4 GPUs. So this is another way to work with us. And yeah, that's it. Happy to take questions.
Yeah, Paul, why don't you come up here and ask your question? Hey, Omer, thanks. That was a really, really cool talk. I have a general question about like ZK acceleration, which is not specific to Ingonyama, which I've looked at and I think is a really, really amazingly engineered library. But something that I think about a lot is the risk of side channel attacks on zero-knowledge proof implementations. And I'm just wondering, like, if you have thoughts about what the role of companies like Ingonyama is in building like constant time or like side channel resistant zero-knowledge proof implementations. And now I grant you that like side channel attacks probably aren't a part of every threat model in zero-knowledge proofs, but like I think like a lot of threat models that I personally care about, they are a real risk. So I'm just wondering if you have thoughts about that.
That's a great question about side channels. So, the problem with side channels is that when it comes to hardware acceleration, I focused here is that they are creating counter effect, right? So for us, adding support for constant time cryptography and so on basically means that we need to move slower, right? So the approach for us is let's start by becoming the fastest we can and then start to deteriorate implementation until we can have this constant time thing. So the only thing I have to say is that I share the pain. It's something that we definitely encourage like hardware vendors to work with us on that. But from a commercial point of view, this is something that gets like priority at the very bottom, unfortunately.
All right. Let's thank the speaker again and. And the next speaker is going to be Andrea from Fortbomb, and he has zero knowledge for identity